Normally, I shouldn't put myself on as a speaker on the first day as one of the organizer, but I knew that Gregory and I would be without jet lag because Gregory is spending some time here and I came from the US. So I put us on for the first day. When I said a few words just at the beginning, of course, the one thing I did forget and I want to mention is great thanks to IMPA for hosting this activity. I'll tell Eduardo as well. So I would like to speak about moduli spaces of polarized Enriques surfaces. And this is joint work with Valery Gritsenko, who originally also wanted to come here, but for some technical and bureaucratic reasons couldn't make it in the end. So let me give you an introduction. And of course, we all know what an Enriques surface is, but just as a warm-up, let me state it again. And everything I'm going to do is over the complex numbers. So an Enriques surface S is a compact complex surface with the property that its canonical bundle is not trivial, but twice the canonical bundle is, and that the irregularity is 0. Well, you know these appear in the Enriques Kodaira classification, and let me just make a few remarks to set things up. And the most important for us is that the two torsion of the trivial bundle immediately gives an étale 2-to-1 cover from a surface X onto S. So it's tau 2-to-1, and it's very easy to work out that this is a K3 surface because the canonical bundle is trivial. Also, the irregularity has to be 0, so it can't be an abelian surface. That also tells us what the numerical invariants are of the surface S. So we immediately get that the Euler number of an Enriques is 1/2 the Euler number of its covering K3, which is 12. And the Betti numbers will obviously B0 and B4 are 1, B2 is 10, and the odd ones have to vanish. And what do we know about the Néron-Severi group? We know that H20, well, it's 20, which is H0S KS, is trivial. So what we get is that the Néron-Severi group is discrete. It's the same as H2. And this is Z10 plus 2 torsion coming from the root of the canonical bundle. And of course, I've got a cup product, which gives that the free part of the Néron-Severi group, a lattice structure. So as a lattice, this is U plus the negative E8. And the U is, of course, the hyperbolic plane here. Okay. So dealing with moduli, we obviously want to talk about period points. Talking about period points means we have to discuss what a marking is. marking. A marking of an Enriques surface is an isometry, say phi, from the free part of H2, which is H2 mod torsion, with this abstract lattice U plus E8 minus 1. And we want to relate markings of K3 surfaces and markings of Enriques surfaces. So let me recall, because you know this, that the K3 lattice is 3 copies of U and 2 negative E8s. And to relate the markings of Enriques and K3, I want to introduce an involution on the K3 lattice. And this involution should be as follows: x, y, z, u, v, where this means the x, y, z are in the capital U and the u and the v are in the negative E8 minus 1. That should go to z minus y, x, v, and u. It will become clear in a moment why this is useful to look at, but for the moment, let me just state what the plus and the minus eigenspaces are. So the plus eigenspace is obviously all vectors of the form x0, x, u, comma, u. And then the x and the u are in the hyperbolic plane of the negative E8 minus 1. So as a lattice, this is u2 plus E8 minus 2, where the 2 means that the intersection form is multiplied by 2. And that's because we have 2 copies here. The eigenspace, and let me call this M, and let me call the negative eigen, this is then x, y minus x, u minus u, and by the same token, this is isomorphic as a isometric to u plus u2 plus E8 minus 2, which I call n, and that's, of course, the orthogonal complement of M inside the K3 lattice. Okay. What else do I want? I have this 2-to-1 cover here, this étale 2-to-1 cover, and that gives me an involution, a covering involution, which I will denote by sigma. And now I can sort of state how we can relate markings of Enriques surfaces with markings of they're covering K3 surfaces. So this is a well-known fact. Given a marking phi from H to S, free part to U plus E8 minus 1, one can obtain a marking, say, phi tilde of the covering K3 surface into 3u plus 2e8 minus 1, such that let me now get this straight. sorry. This is the phi tilde, this is the rho. In other words, I can find a marking of the K3 surfaces which is compatible with the involution which I've got, with the involution sigma. So what that means in particular, if I pull back the H2 of the Enriques surface, it now becomes part of the K3 surface, the H2 therein. And now this, if I apply phi tilde to this, then this identifies the pullback of the Néron-Severi of S with my lattice M. That is the point of this construction. Why am I doing? Yeah. Sorry? Sigma is the covering transformation. This is P upper star. P was the map from X to S. So I pull it back to X. And sigma was the map from X to X, which sits over the, which is the covering involution of X goes to. Okay. Okay, so let me look at this lattice N. So the signature of N is 2 positive and 10 negative eigenvalues. And then we can associate to it a homogeneous domain. And I'll say in 1 minute how this is related to what Gregory was doing. So, sorry, let me call this omega n, which is all points in the projective space in tensor C, with the property that x comma x is 0 and x bar is positive. So this is 12-dimensional, so this is 11-dimensional. I have a quadratic equation, which is one condition and then an open part of it. So this is a manifold of dimension 10. And this is general theory for for signature 2n. This will be a copy of 2 disjoint connected components. And the relationship with Gregory's result is that dn is the Hermitian domain associated to, well, his notation was G for the real group. That is the S0 to N. I'd probably better take the identity component of identity. And the maximal compact subgroup here is SO20 times SO2N. But here we have a nice complex manifold, so we are in this situation, which was discussed in the previous talk. Okay, now let's say we have on omega S, let's be omega x, let that be the 2 form, the non-zero 2 form, unique up to scalar on X. Now I have the covering, and I can ask what the covering map does to this 2 form. And of course, since we have no 2 forms downstairs on the S, this cannot be invariant. And we must have that sigma star of this 2 form is minus omega x. So this is a non-symplectic involution. And again, the reason is that we have no 2 form on the Enriques surface. So now if I look at my marking, I extend it to C, Let's see what it does to that point given by omega x. Then now this becomes a point in omega n, because this is in the -1 eigenspace. And nothing really stops me to put that into dn. So this will become the period point of the marked Enriques surface, which is really a period point of a K3 surface. Okay, so that's that. And then I need some groups. So the n is there, that will play a major role. So let me talk about some groups. The ON is the integral orthogonal group of my lattice n. Of course, that will act on omega n. And now it can happen that some elements will interchange the two components and others won't. Yeah? And I look at the subgroup which fixes the components. That's typically called O plus of n. This is all G in O of n, which fix the components. And a more fancy terminology for that is these are the elements of real spinor norm 1. But that is an index 2 subgroup. And now the point is that the O plus of n, this now acts on this homogeneous domain n. So if this is the gamma in Gregory's talk, we are in the situation of Gregory's talk. And by the way, if you are in this, if you take this group and you ask about the fundamental group, then the answer is you get a simply connected toroidal compactification. This is something we worked out at some point together with Gregory and Valery Gritsenko. This just as a side remark to connect it up with the previous talk. So let me put EMEN as O plus n, well, dn divided by O plus n. And this is where the period points of marked Enriques surfaces lie. And throughout, my notation will be an ordinary M will be a modular variety, meaning a homogeneous domain by some arithmetic group. And later on, I will use the \Mathcal M, which then will be moduli spaces. Yeah? So, because the things will be related, so this is, so if I write once this and once that, it has a meaning. It's not just that it's sloppy handwriting. Okay, now we need something else. We have to take out a divisor. So let me take delta in n, a root, so an element of order -2. And note O plus n acts transitively on all roots. And what I can do is, well, I can either say this is a reflection and take the associated hyperplane, or I can take HD delta, which is this set of all x, such that x delta is 0. So this is something which I can think of in dn. And that, if I map it to my quotient, will then be a hypersurface. Okay. And we take this hypersurface out, and we get the following well-known theorem. The open variety MEN0, which is MEN minus this hyperplane, corresponds via the period map bijectively to the isomorphism classes of all Enriques surfaces. Okay. So often this space here is referred to as the moduli space of Enriques surfaces. Now, this is perfectly justified in the sense that the period map defines a one-to-one correspondence of the points with the isomorphism classes. However, and that's a point I would like to stress, is this is not a moduli space which, in the way we normally talk about moduli spaces in algebraic geometry. So this is not something where you say, write down a functor, yeah, and then say this functor is represented by a coarse moduli space. This is not the case here, and I don't think you can make it to work that way. So yes, it has that meaning, but it's not a moduli space in the sense of algebraic geometry. And one of the reasons is that automorphism groups of Enriques surfaces do all sorts of things and jump and can be infinite. You know, there is a lot of issue. I mean, even on the stack level, Liedtke sort of looked at this on the stack level. This is not even an Artin stack. Yeah? So not a moduli space. Anyway, still an important variety, and we know something about it, and this is a result of Kondo, that this space is a rational variety. And in the spirit of Gregory's talks, I would like to ask the question is, if we take this moduli space, yeah, if we compactify, say, well, we remove the delta minus 2 and we compactify it, what is the fundamental group? That's something I don't know. So if the hypersurface is there, then it's a simply connected manifold. So take out that one hypersurface, what is its fundamental group? Yeah, you compactify. I mean, well, compactification makes a difference to the fundamental group.
Yes, okay, but depends then how do you compactify?
Well, in the sense of Gregory, take a smooth, a toroidal compactification, which is normal, yeah? And then it's a well-posed problem.
Then d minus 2 is the way inside.
Yeah, the delta minus 2 inside, but you can take the closure. Yeah? I mean, if you want, I think you can first compactify and then remove the closure of that hypersurface, I think. Okay. So I hadn't really planned on saying that, but I don't think it matters. More groups. So whenever we have a lattice, let me take an even lattice, Then we can look at its dual lattice. And we can look at the discriminant of L, which is L dual divided by L, which is the discriminant. And still, this comes with an induced quadratic form. And then what one can do then, and let me write it down for M and N, I can take, so the two lattices which I was looking at is U2 and E8 minus 2, and the N was U plus U2 plus E8 minus 2. And of course, you see that in this case, the dm and the dn are naturally identified. And this is f2 to the power of 10. And the orthogonal group that is the even orthogonal group of F210. In characteristic 2, one has an even and an odd orthogonal group. It's the even orthogonal group, and it's quite a big group. Its order is 2 to the 21 times 3 to the 5 times 5 square times 7, 17 times 31. And of course, we can project our group onto the orthogonal group of the discriminant. So we have our ON. We can project it to here. And in this case, it turns out that this will be surjective. And then I can look at the kernel. So this O tilde n is defined as the kernel. This sequence is its definition. And this is often called the stable orthogonal group. And the same similarly for O tilde of M. Again, there this map is surjective. I can take the kernel. And the last group I need, I think at least for the time being, is the intersection of that group with O plus. And again, this will now act on our homogeneous domain Dn. Okay. So what we do now is, now we fix, say, a primitive h in U plus E8 minus 1, which is my M. So what I'm aiming for is I want to construct moduli spaces of Enriques surfaces, of polarized Enriques surfaces, real moduli spaces, and they depend on polarization. And you should think of that as the polarization in the Néron-Severi group. Yeah, that's what you should think of. And then we can look at OMH, which is the set of all G in OM, which is the same, by the way, as GM 1/2. I mean, the scaling of the form does not change the fact that it's an isometry in any way. So let's look at the stabilizer. So this is a subgroup of OM. And what I can do is the following. I can project this down to the orthogonal group of the discriminant. I can take the inverse image of that, going back to n, and I call this gamma h. And that now sits inside O tilde n, contains O tilde n, and is a group of On. So this is an arithmetic subgroup. And I said this is the last group I wanted to define. I was wrong. We take gamma h plus, which is gamma h intersected O plus of n, and that again acts on the n. Okay? So you have a group, you project it down here, you identify. Okay. The question is why one should do this. Okay. So let me now put M, E, N, H as the quotient of dn by this group. And that maps to the moduli space in inverted commas of Enriques surfaces. This is finite, but it's not a Galois cover because this gamma h is in general not a normal subgroup. But still, I've got the finite map here. And then recall I have my delta minus 2 here, and I just pull this back. And then one can show, but this is not immediate, that this is still an irreducible hypersurface. The fact is that even the reason is that even O tilde acts transitively on the set of all roots. So, okay. That is the definition of this. Now I have to talk about, this is the most technical part which is coming now from the Latin.
Sorry, just one minute. This is the covering, it's not covering, okay, covering that is not covering for which the pullback is still irreducible.
No. Sorry, I didn't say that. I mean, I have a subgroup. Yeah, the subgroup gives me a covering. I have this hypersurface in here. I take its inverse image. I can do that for any covering like here. The statement is this hypersurface is still irreducible. It's not the biggest. I could have taken out here O tilde, which is an even smaller group. O tilde. So my gamma h contains O tilde. No. If you take O tilde still acts transitively on all roots in n. Yeah? So it still remains irreducible. This is a finite degree. Yeah. It's a finite degree. Yeah. Now I have to talk about V in n be a vector of length minus 4. Now these vectors we can be even or odd depending on whether VL is 2z or z. So this is the ideal generated by taking the product of any element in n with V. Okay. O plus n acts transitively on all even v of length minus 4. So again, this gives me a hypersurface in this space. And this has a geometric meaning. If you think of that parametrizing Enriques surfaces, then this hypersurface, which is 9-dimensional, parametrizes the so-called nodal Enriques surfaces. Nodal Enriques surface means that we have a rational smooth curve in it. Yeah? And that's a hypersurface in the space of all Enriques surfaces, and that's described in this way. Now, I do the same, so my delta minus 4 is also in here. Again, I take its inverse image. I do not claim that this is irreducible. This will, in general, then split up in a number of components. And what's interesting for me, for my geometric applications, is part of that divisor. And that's a bit technical to explain that. So if you recall that the n was all vectors x, y minus xu minus u, which is u plus u2 plus e8 minus 2, and I say I want to put delta xu, and then there's the following fact. If delta in u plus e8 minus 1 is a root, then delta, or let me say delta prime, which is delta prime and minus delta prime, and I think of that as sitting in n, in an obvious way, is an even minus 4 vector, and this gives all even minus 4 vectors. Yeah? And now I want, with respect to my smaller group, gamma h plus, consider the orbit of all such vectors bits of all such vectors modulo gamma h plus with the property that delta prime dot h, these are both elements in m1 half, is 0. So the result is this gives something which I should have put even here. Yeah. So this figures out or singles out some components of this delta minus 4h even. So that can have several components, and this process I described to you figures out some of these components, but in general, not all of them. I know this is technical, but I needed to describe the result. And then let me put two spaces, and I'll do that over there to keep them on the board for a while. So now define, and I'll come to that in a minute. M E N H num, which is M E N H minus 2 divisor minus the even minus 4, where I take out this hypersurface, which I've union of hypersurfaces which I've described. And I can also define M E N H N N, and this will be explained why I chose this notation as M E N H minus delta minus 2H union all even here. And then the situation is that this here is an open part of this MEN num. Okay, good. Those are the spaces. And of course, I did that with a reason. And the reason was that I want to describe moduli spaces of polarized Enriques surfaces. So let me step on to the next section. This is now about moduli spaces, and it's clear what we want to parameterize or classify. Definition A, well, polarized or semi-polarized Enriques surface is a pair SL, where S is of course Enriques, L is a line bundle, and I want that the line bundle is either ample or semi-ample. Semi-ample, I mean big and nef. So the image is something like Enriques surface with a few nodes. That's the first definition. The second definition is a numerically semi-polarized Enriques surface is a pair SL bar, where the L bar is the class defined by L in num of S, which is NS of S modular its two torsion. Okay? And we are asking about moduli spaces in the usual things, so I should tell you what the polarization is, a type of the polarization. Is an OM orbit of a primitive vector H in M1/2, which is U plus E8 minus 1. And this is the Néron-Severi as an abstract group modulo the two torsion. So of course now you know why I looked at these h's. Yeah, that is where it comes from. So this is a situation which has been dealt with in physics general theory, that these are, that here we have moduli spaces. By physics theory, we have a moduli space, coarse moduli space, say M, E, N, H, A, polarized Enriques surfaces with a polarization of type H. That's a quasi-projective variety. And of course, I would like to describe it in terms of modular varieties. Now, what we have, of course, is we have an involution on that moduli space, which maps, say, SL to SL tensor K. That's an involution, and it's, well, without fixed points. And I can take the quotient of this involution, H num, is just the quotient of this Vivek moduli space by this involution. Now the question is, and of course the answer will be yes, because that's the way I set up, can we describe these moduli spaces in terms of modular varieties? Answer is yes, and the result is the following. Why H is primitive? Well, I mean, if it's not primitive, of course you can ask the moduli problem, but you won't get anything new because you can always divide that polarization by some d. So without loss of generality, you can assume it to be primitive. And say if you are in the situation of K3 surfaces, yeah, then the type of the polarization is just the degree, yeah, because that will define the orbit of the vector, yeah. Here it's much more complicated. Yeah? The degree, the h square, is there, but for the same degree you can have many different types of polarization. So the degree does not define the orbit under the orthogonal group. But that's a phenomenon which also comes up for the IHSMs. But it's even more so, much more so here. Okay, so here is the result. Theorem. There exists a morphism which does the following. MENH, factoring through a 2-to-1 cover, and the important point is that this is isomorphic to this modular variety, which is described to you before. Okay? So that's the result. Yeah. And secondly, maybe the open part M, E, N, H, N, N parameterizes the non-nodal numerically polarized Enriques surfaces. There are actually two questions here to which I do not know the answer. I have this 2-to-1 cover here. I do not know in general whether this is trivial in the sense of two disjoint components or whether this is connected. So question 1 is MENHA always connected? The answer is yes, in some small degree cases, but in general, it is not known. Now, the moduli space of numerically polarized Enriques, that is a modular variety. So the question is the moduli space itself a modular variety? Then, of course, it would be connected. So in other words, maybe I've just written down that group gamma H plus slightly wrongly in the sense that I should have taken an index 2 subgroup and I get the moduli proper. I don't know. I'm not really sure that that's the case, but I don't know. There is something which Kondo and people have worked on supermarked Enriques surfaces, which is certainly something to do with this, but I don't think, well, they can't answer these questions either. So these are genuinely open questions. And I mean, the idea of the proof is once you sort of set it all up is essentially everything comes down to the Corollary theorem for K3 surfaces. Yeah? You just have to work it out in detail. Once you've written down the right definitions, that part is not so hard. Let me make two remarks, or let me say a corollary, which maybe is a little bit more. Yeah.
But question 2, no?
Uh-huh. Yes.
All them are conjugates. I mean, it's
yes, but
not easy, but doable check.
If you have a way of checking that the 2-to-1 cover, you get that way. I mean, you have to do something which is an unramified cover. So you have, I mean, not as the modular variety itself, but the ramification has to happen on this delta minus 4, blah, blah, or delta minus 2. So that would be the first condition on the group. And then the question is there a way of relating it to the moduli of Enriques surfaces? So, yeah.
Okay, the first problem that would be doable.
The first, yes, I fully agree, yes, yes. Yeah. Okay, and then if I look at, elements, what I've taken out here, if you do not remove that divisor, you get semi-polarized Enriques surfaces. That again is like in the K3 case, but at this point I would prefer to stick to the to the genuine polarizations. Now there is a following corollary. There are up to isomorphism only finitely many not a good way of formulating it, isomorphism classes of polarized Enriques surfaces. So if you think of the K3 case, so if your degree goes up, you get a sort of infinite series. And I'm not sure I can state saying they're all different birationally, but I bet they are. Yeah, there's no reason why they should be related. But here there are definitely only finitely many isomorphism classes of, moduli spaces of And why is that so? Let me give you the proof. The first remark is there are only finitely many subgroups which lie between the O tilde and the O. It's a finite index, finitely many possible subgroups. And then, okay, you remove some hypersurfaces. These might still depend on the on the H itself. But the next remark is that delta minus 4H even has only finitely many components. And now you could say, well, okay, that gives us the result for the numerically polarized K3s, but why couldn't it be that these things have infinitely many different double covers? The answer is this. These spaces M, E, N, H, num, num, have the homotopy type of finite CV complexes, and H1 of these things with coefficients in say mod 2z is finite. I learned that from Eduard Loyenga, and hence it seems well known. Hence, there are only finitely many étale double covers. Okay, so that's that. So that's, I think, may have been sort of guessed by some specialists in Enriques' surface, but I think when I first realized it, it came as something of a surprise to me. Okay, so now, of course, we are in the situation, as Gregory said, I mean, there are natural questions one asks. And one of the natural questions one asks here is, what is the Kodaira dimension of these moduli spaces? And let me do this as my final remark. So by the way, sort of as you know, we've scheduled these things a bit unevenly. I mean, the talks have slightly different length according to what the speakers said they would like. So you're in for 75 minutes in case you haven't read the program. So a bit more. Whether I'll need the entire 75 minutes is another question. Well, let's see about the Kodaira dimension, at least of these modular varieties. Okay. Proposition. If H square is less than 32, then the Kodaira dimension of, let's say, M, E, N, H. And now it doesn't matter what I take out. I mean, here we're talking about something birational. So just let me stick to these modular varieties here. Is minus infinity. The same is true for degree between 34 and 42, with one possible exception in each degree. So as I said before, like in the Kodaira, in the K3 case, you're used to saying the degree, and that gives me the moduli space. Here, you have to fix the type of the polarization, this orbit, and the degree anything but fixes that orbit. So if the degree goes up, the number of orbits grows quite a bit. Finite, of course, but it grows. And again, in these cases, there's always more than one orbit. So here we claim it for all orbits. Here we have to remove one orbit. And let me give you the idea of the proof, because that fits in with our activity. And this is where modular forms enter. So let omega f 10k f 10k times dz k be a pluricanonical form. Yeah? I mean, all the pluricanonical forms come from modular forms. So that is a modular form. It should be a cusp form, but it doesn't really matter at this point. A modular form of weight 10k. Now, one thing I know about this modular form is that it has to vanish along the branch locus. Otherwise, it won't go descend to a pluricanonical form on my modular variety. And f10k has to vanish along the, I should say, ramification locus of the period domain to this modular variety. And one part of the period of that branch locus is, okay, now let me write it this. This is, I can write this down explicitly, R, which is the union taken over all plus minus R in N, with the property that this has degree -2 or -4, and that the reflection generated by R is in the group gamma plus. So this is the reflection given generated by my root or my -4 vector. And each of them has an HR, yeah? has a hypersurface which is orthogonal to that. That is the ramification locus. It will contain the -2 locus. And then there are modular forms. And some of you here know more about these modular forms than I do. One is a phi 4. 4 is always the weight. So that's a modular form of weight 4 with respect to O plus n and a character of order 2. And it has the property that it vanishes exactly on the union of all of these -2 hyperplanes. Okay? You look critical? Oh. Yeah. You have worked with that, haven't you? Okay. And then there is another one of 1 degree of weight 124, I think that. I think people refer to that as a Borcherds form. It's not the famous phi 12, but it's similar in spirit. So that is something of m of weight 124 in O plus n. Again, with respect to a character of order 2, but a different, and the divisor here dn is the union of all hyperplanes. The union of all hyperplanes of even -4 vectors. So what I can do, what one then can show is that the F10K, this vanishes on the, must vanish on the -2 divisor, as does the phi4, and it has to vanish here even of order k, because we've got k-fold pluricanonical forms. So what we can do is, we can do F6k, which is F10k divided by phi4 to the power of k. So that is in M6k, plus gamma plus n, some character which I don't want to specify here. Now the next thing which we do is now symmetrize F6k with respect to gamma plus. So what I want to do is I want to define F sim of Z as the product over all G while running through essentially the conjugacy classes F6k of Z. So this is some modular form where it can be computed in terms of the groups. And now let M be the multiplicity with which this form vanishes on H minus 4H even. And this can be computed in terms of the roots which are orthogonal to my polarization. So this is where the special form of the polarization comes in. Somehow this can be computed. And then let's look at F, or let's look at G, which is this F sim divided by the phi 124 to the mth power. Oh, I can do that, and this is still a regular form. But now, in this group, in the situation which I am in, I can compute the weight, and that becomes negative. And of course, that can't happen. So in other words, we can't have that pluricanonical form, so there are no pluricanonical forms. I mean, that's a sort of standard type of argument which one often uses, but it comes here with a slight twist to it. Yeah? So that's what we do here. So there are moduli spaces with negative Kodaira dimension, quite a lot of them, in fact. Of course, in some cases, one knows that before. So remark, classically, well, so known for H square 4 and H square 6. In each case, there are two types of polarizations. One is base point free in each case, so that's the one I take. That's what's often or sometimes referred to as the Cossack-Werra polarization, and that is the one which gives the classical description of Enriques surfaces are sitting in P3 being singular along the edges, the vertices and edges of a tetrahedron. And that case, due to Kasnati, that case I think was Jean Badronachev. But there are a number more, but we only know negative Kodaira dimension. We do not know at this stage whether they're irrational or not. Let me state another result. Proposition. There are types of polarization H such that my MNH becomes MEN2. This is referred to as the modular base of Enriques surfaces with a level 2 structure, which is O tilde plus of n modulo dn. So Enriques surfaces with a level 2 structure. And this space, by the way, this space dominates all moduli spaces of numerically polarized Enriques surfaces. But that exists. So the reason for H square big enough, one can find H such that the orthogonal complement has trivial orthogonal group. And then one immediately sees that the gamma H is the stable group. Now the interesting part is that this one here is of general type. And this was Valery Gritsenko explained that in a talk at the Schemanikov meeting last year, so where he gave a proof that this moduli space is of general type. Now, this is the numerically polarized, but of course, if you take a 2-to-1 cover, it stays of general type. So in particular, there are moduli spaces of polarized Enriques surfaces. Which are of general type. And I think that comes as a surprise. I don't think it's ever been officially stated as a conjecture, but many people working on Enriques surfaces sort of said it also in talks, that there was a feeling, hope that all moduli spaces of polarized Enriques surfaces were unirational or something. That is definitely not the case. So relating it to this Gritsenko result, there are moduli spaces of these polarized Enriques surfaces which are of general type. Okay, so my time is over, and this is where I'd like to conclude. Thank you very much.